All right, very good morning. Welcome back. Let's move on to part two of the topic of electromagnetism. Now, for this topic itself, we had initially understand what is the magnetic effect of a current in a wire. So when you have a wire, let's say this is a wire itself, and this is a wire, you know that there's a magnetic field that moves around it when a current flows through this wire. So what happens now is this chapter, we're going to take this wire for current flowing through, and we're going to place it in a magnetic field. Oh, okay. So when we take a current and we place it in a magnetic field, okay, what will happen is there will be a force being produced. Okay, so this is what we call as a motor effect. So let's start. Force on the current carrying conductor in a magnetic field is called a motor effect. So what happened is I have a wire that carries a current and I place it in a magnetic field. What will happen is the force will be observed, and we'll use this diagram to demonstrate the effect. Okay, so there are a few things here I want to do. When I mention current, I will use the symbol I. When I mention magnetic field, I'll use the symbol B. Okay, and when I talk about force, I'll use the symbol F. Okay, so this is what happened. There is a wire here. So this is the wire here. The current flows downwards, flows in here, flows out, and then it goes out. So I believe it flows this way and then it flows out. All right, so that's the current, how it flows in the wire. This is the current carrying conductor, the wire. Now you place in the magnetic field. So this is the magnetic field, north here, south here. So what happens to the magnetic field? The magnetic field goes this way, upwards. Okay. So what will happen is now we want to identify the force. So in this case, we down here it shows that this thing is being forced up this way, or we can say that this bar or this wire experience a force this way. That's why it's being kicked out. Okay, so let's put all this into perspective. Current goes here. Okay, magnetic goes here, and this thing is being kicked out and goes here. Oh, let me redraw this again. And the force goes here. Now then you'll ask, but Mr. Song, how is this perpendicular? Now you must remember this is three-dimensional, okay, three-dimensional. So all of this is actually 90 degrees from one another. Okay, this is three-dimensional X, Y, and Z planes, so they are all perpendicular to one another. Okay, so once we know this itself, we can actually bring in a Fleming left-hand rule. So take out your left hand, left hand. To deduce the direction of the current, we use Fleming's left-hand rule. Right, this is different from your right-hand grip rule. You must be able to state Fleming's left-hand rule before we use it for any explanation in your worksheet. Okay, so how do you remember this? Fleming left-hand rule, take out all of them and make sure they are all 90 degrees to one another. Okay, all right, 90 degrees all for one another. Before you do this, you want to do a bit of stretching also. There are people who have hand cramps also when they're doing this. So what we want to do, your thumb will be force F, your index finger will be B, which is magnetic field, and your second finger will be current I. So how do you remember? I like to remember as FBI. It's like the police or in America, FBI. So FBI, and they all must be 90 degrees. So if we were to apply this in our previous part, the current goes from B to C. All right, the current goes here, FBI. So I is the bottom one. So that's the current. B goes upwards and I will kick it out. Okay, so you can try it. Pause the video here and try it first to see that you're able to get your force, which is in this direction, kicking outwards. Okay, all right, so let's take a look here and let's try it. So north to south, let's draw the magnetic field first. The magnetic field goes from here to here. Your current goes here to here. They want to see your force. So you don't have to draw your magnetic field, but I just draw here to illustrate so that's easier for all of us. FBI. So B goes this direction. I goes into the paper and F will go downwards. So if I were erase my magnetic field because I do not want it to get lost. So this is my force. Okay. So Y, magnetic field goes this direction. B, your current flows in this direction. I. So FBI, it goes downwards, which is your force. Okay, good. Let's take a look at the next part. Now, instead of having a wire, because just now here itself, you can see that they use the whole wire. You can see this is the whole wire here. In the exact practice that we do, can you see this is also a wire? But we do not have to put the whole wire inside. We can also just simply put a charge. Okay, we can simply just use the charge. Now recall that when we talk about a conventional electric current, we are always talking about positive charges. So when we say current flows, when we talk about current or conventional current, we are always talking about positive charges. But sometimes the question will also ask you, what happens when electrons, which are negative charges, they flow? So you must understand that it's in the opposite direction. Okay, so whenever we talk about current, we assume there is a positive charge. Electrons will be in the opposite direction. Okay, so let's clarify this once and for all. So now, let's recall previously when we talk about the positive and negative, not positive, when we talk about flowing in and out of the paper. So when we have a cross, it means that it's going in or away. When there is a dot, it means it's coming towards or out. Okay, so let's clarify that first. We will use Fleming's left hand rule here, and let's see how they actually behave. So now there is a positive charge that flows in. So the charge flows this way. This charge, when it flows this way, because it is positively charged, we can also call it as a current when it moves. Okay, so it's a conventional current. So when the charge moves here, the magnetic field goes inwards. So you can see that your magnetic field goes inwards. This blue color one is your magnetic field. Okay, your current flows this way. Let's identify the force FBI. B goes into the paper, I goes towards the right, and the force will go upwards. So that is why your charge will experience a force upwards and it will start to turn because it experienced a force upwards. Okay. Alright, let's take a look at the next two. Predict the direction of the force acting on the beam of electrons when you enter it. So now this is not a positive charge. This is not conventional current. This is an electron or negatively charged. And it says that it moves this way. Okay, but this is your electron, so we cannot do it this way. We got to flip it. We got to say that the current flows this way. Okay, so let's use B goes in, F, B, I. So B goes in, I goes back, force downwards. So your this thing, this charge, sorry, let me draw it nicely. It flows down. Okay, so the force is downwards. Next, positive charge. Now your FB comes up, current flows here. FB, B goes in, no, B comes out, I goes to the right, it goes down. Force. So it falls down. Okay. Forces between two parallel current carrying wires. So now you're going to take two wires, both have magnetic field, both has a magnetic effect on each other, and we're going to see how they behave. So the general rule of thumb is if we place conductors carrying current in opposite direction. So let's say if I have two wires, one current flows upwards, one flows downwards. What will happen is if they are in opposite direction, they will repel. Now, if I have two currents that flows in the same direction, they will attract. So these two will repel, these two will attract. So let's find out more about how they actually behave. So uh, we have one current that's going out of the paper and one current going in. So when we go in, use your right hand grip rule where the thumb is the current flowing inwards. The fingers will give the magnetic field. It flows in the clockwise manner and the other one flows in the anti-clockwise manner. So once you combine, you can get the electric field pattern as such. But what next thing we want to know is, let's consider each one on its own. So let's consider the magnetic field of the current going in. So let's take a look at this one. So this will generate a magnetic field that it goes in this direction. That means this wire here will experience a magnetic field that is upwards. So let me remove this. Okay, why? Because this wire here gives a magnetic field when this one place is in the magnetic field of this other wire, it has a magnetic field of B upwards. So if we use our F, BI, remember it's the left hand, B up there, I coming towards, we will see that this goes in this direction. So that explains why the force goes towards the left. Now, if you repeat the whole explanation using Fleming left hand rule for the other, this wire goes down, means that the magnetic field is here. FBI go in, see that the force goes here. So as you can see, if they're in opposite direction, they will repel. Okay, next. We can use the same argument, and in this case, we'll see that they actually attract and the force goes in. And this will be the magnetic field pattern that is shown there. All right, you can do through the whole argument itself and deduce why they actually move in the same direction. Take note that these two forces on the wires are actually an action-reaction pair based on Newton's third law. Yeah, action-reaction pair of forces. Okay, so with that, we'll end this chapter here.